Thank you everyone for coming, and Cambridge time, 5 past. So we're super excited to have our guest speaker today, Silvia Zuffi. She is amazing researcher and has been working on 3D reconstruction of humans and animals for the past decade, and has done a really amazing work on basically setting up the foundation of these model-based reconstruction of 3D humans and 3D animals. And did a PhD from Brown University with Michael Black. And that was before Michael Black moved to MPI. And it was like we've been working together on these animal 3D reconstruction and had several workshops at CEPR. And it's really, really excited. Pleasure to have Silvia here today sharing with us her work on 3D animal reconstruction. Silvia, do you want to take it?
Yes.
Yes. And
I'll turn this on. Okay. Thank you very much for the introduction. And I'm super happy to be here. I should have done this a long time ago. Today I'm going to talk about my work on cross-species 3D animal model-based reconstruction. I want to start showing this slide. So this is a picture from the Global Risk Report of this year. This is from the World Economic Forum, which happened recently in Davos. And in this report, the authors, they interview a panel of experts, several hundreds, and they ask what would be the major risks, choosing between a set of risks in these 5 categories: economic, environmental, geopolitical, societal, and technological. In a short-term period, 2 years, or long-term, 10 years. And here you can see that in a long-term period, the first 3 major risks will be related to the environment, with biodiversity loss and ecosystem collapse in the second place. This was actually similar to the report from last year. So this is, it's still the... Here was a recording, okay. Yeah, so this kind of justify working on these themes of biodiversity preservation if there was a need to do an introduction on motivations. And from my point of view, what I ask myself is what can computer vision do to help fighting this biodiversity loss and ecosystem collapse? There are many things we can do on various, topics, species. What I'm mostly interested is looking at animal behavior. So we know that when we have a behavioral change, this can be an indicator of a population decline. And for animals, for articulated animals, studying behavior essentially means to look at animal motion. Because many animals, they actually communicate a lot with a sort of body language. As humans, we have evolved with a very rich language with a lot of structure. For animals, there are some cases vocalizations that are mostly context dependent, and a lot is left to the body posture. And this behavior is also influenced by the environment, which is in computer vision is not often taken into account. So what people have done in the past to look at animal motion to study behavior is to look at the pattern of motion of significant markers, landmarks that are located on yeah, but then can you? Oh, it doesn't work.
Normally you can change it a bit because I've noticed if it's too close, it starts to make that.
Yeah, but then I have to find here maybe.
Do you not change the length of it?
Yeah, can do that. Like this? Can you hear me? Is
I
it
think that
perfect?
would be,
Okay.
hopefully.
I had the impression it's not working, but if you say it's okay,
This is good.
it's good. Okay, thanks.
And Elliot can tell if it's coming okay through Zoom.
Yes, I'm just gonna click this one. There you go.
Sorry. Okay, sorry for that. Yeah, I was saying that you track these body landmarks in a video. And as you can see, this is really an image-dependent representation that really depends on the relative geometry between the camera and the object, the animal, which is perfectly fine if you are in a controlled environment, like in a lab. But if you go outside, and capture animals with a drone, so you have a moving camera and the animals are moving, and then this 2D representation is not really useful, because for the same action, you would have a completely different set of motion of the body landmarks. So what I think we should do, and this is what I've been doing for the 10 years already, is to take a 3D model-based approach. First of all, research questions are mostly formulated in an animal-centric representation and not in an image-based representation. So you want to describe motion, maybe you describe how a skeleton moves, and shape is related to the morphology and not as a pattern, as a 2D landmark pattern. And if you look at what we can do with this information, in dealing with resource management, often we need to simulate events because we might create predictive models. And to simulate events in the physical world, we need to perform this explicit 3D modeling and reconstruction of the object and of the scene. And I think if we can do this 3D modeling and then do really a meaningful simulation that recreates in a realistic way what the animals are doing, I think we have really understood animal behavior. And we are really far from this. Okay, to put in place this 3D model-based approach, we need a way to represent animals and the surface of animals and their skeleton. So essentially, we need generative models of animal 3D surface that are driven by a small set of parameters. And typically, for articulation, we already are in this regime of a small set of parameters because we represent articulation with the rotation angles of the body parts. For the surface, we might represent the surface, as in this case, with thousands of points. And to reach this low-dimensional representation, we need to compress these thousands of points in a low-dimensional space. And once we have this model, this is really useful because differently from the 2D representation, now we have a surface, so we can also reason about contact, about the interaction with the environment that I said is important. We can do unsupervised learning if we generate the animal as it looks like with also the texture. We can do volume analysis, weight estimation, and so on. So typically, this model of animals has this form, at least in my work. So we start from a template, which is a reference for shape and pose. And then we apply the deformation to the surface to obtain the animal we want. In this case, we want a cheetah. So we transform the shape of the template, UT, adding vertex displacements that are driven by this set of parameters, beta, that are low dimensional. So typically, I don't know, maybe 40. And then once we have the cheetah, we apply the articulation. So theta is a set of rotation angles of the body parts to obtain the animal in a specific pose. And then in computer vision, we need to find ways to go from an image, estimate the beta and the theta, and obtain the 3D reconstruction of the animal. This has been done already 10 years ago, 2015, for humans. Michael Black and his group, they introduced this model, which is called SMAL, for Skin Multi-Person Linear Model. In the animation, you see different, the gender neutral, the female and the male body model. And you see how realistic this is. It can represent different identities with a post-dependent shape deformation. And this model has been trained by capturing people in a 4D scanner, as you see here in this picture. And it also comes with a lot of motion data that has been obtained by fitting the model to mock-up markers. And it has been used in computer vision from a lot of groups and also from a lot of companies. They even created a company for the commercialization of this model. And despite this look like a model without clothing, without hair, it's really quite used for capturing people, also in interaction with other people, and so on. And then, as I said, the model is trained by capturing 3D scans of thousands of people in a reference pose, and learning this model that I was mentioning before, that allows you to go from a template to any ID by specifying a set of shape variables, betas. And this comes from this template is the average in the training set, and this linear model is computed with a PCA, and here you see the principal components. So the first one, they capture the larger variation in the data, and then small details variation. Okay, so we wanted to do something similar with animals, and for animals, we have an opportunity for capturing animals only restricted to the domestic ones. So for some species, like for example dogs, I think dogs are quite interesting because even if it's a single species, we have a lot of variation, shape variation, and so we created a few years ago a model for dogs similar to SMAL by scanning toys of dogs. And we consider about 40 scans of different breeds. So differently from the people that were standing in the scanner in a reference pose, here we had to take the scans and then put them in a neutral pose, and then do the PCA to learn this low-dimensional linear model, which was a kind of interesting problem, registration problem itself. And now that we have this shape space, here you see this one is the average in the training set. And these are the principal components. So the first one is size, and then you have all the other components. And for dogs, if we sample a random set of betas, we can obtain a dog that might be an interpolation of different breeds, which completely makes sense because you can have mixes. We also use the model to estimate 3D pose and shape from images with this method that is called BITE. And here you see a few results, reconstructing animals from a single image with also complex poses. And this was obtained by looking at the contact points as I said before, this is possible because we have this volumetric, this surface representation. So this was with toys. More recently, this was done before. We actually created a 4D scanner for animals, big animals. And this is the first 4D scanner for horses, and is in Sweden, where they have access to a lot of horses. Not easy, but doable. You see here, so we scanning these horses is harder than for humans because there is a larger variation in size. So this is, I think, is the smallest horse that we have. You see, this is the same person wearing the same clothes, and this is the smallest horse, and this is the biggest. And just look at the size of the head of this guy, and to me, this is impressive. And also, we have very well-trained horses that can run on spot. So these are dressage horses. So we can also capture the formations during this. They cannot really run inside the scanner because the area is not big enough, but they're very, very well trained. We have scanned so far more than 200 horses, so we have kind of saturated the horses that are viable near the university, so we're planning to move the scanner to have more subjects. And then again, we did what we said before, registration and posing PCA to learn the shape space and represent different horses with this linear model. Here, with respect to the toys, the registration is a lot more challenging because we have noisy data. When the horse is black, the scanner doesn't perform very well, and then often you need to have a person that holds the horse, so this creates occlusion. But we created this model that is called Varenne. For Italians, this has a lot of meaning. Varenne is the most famous horse in Italy. It was really a champion. It's written Varenne with also another N and E. But this here stands for very accurate equine network, and realistic equine network. And this is the shape space. And you see that this is our average horse. And again, we have the biggest variation for size and other direction that capture even the different head size from the Spanish horses and the Arabic horses. So it's a very high resolution model. And also, what we did with Varenne, we also represented the post-dependent deformations. We didn't this for the toys, of course, because they are rigid. But now that we have these 4D point clouds, we modeled the deformations, and we did this by modeling the muscles deformations, which I thought was an interesting thing to do. Not going into the detail of this, how we did this, but for the muscle deformation, we saw that modeling the muscles, also with respect to the approach that is considered for the simple model for humans, we do better. In particular, when the horse moves the neck, and these are like maybe the largest deformation that you can do in the 4D scanner. And also what is interesting is that in this deformation model, we can look at what is the body part that mostly affects the deformation of the muscle. And this is like, you see here the colors of all the body parts that we have. And here I'm coloring the muscles with the part that mostly affects the deformation. We haven't really analyzed if this makes sense, but I think it's interesting to look at deformations in this way. Okay, this was a big introduction, but and this approach for horses is very expensive, and of course it wouldn't scale to any species. We have seen recently a lot of data sets that are multi-species, because sometimes I think you want to detect the eyes of a zebra, but then if you know how to detect the eyes of a horse, maybe you're halfway there. So you can put together images of different animals and then learn detectors that are multi-species, and they kind of exploit the similarities between the different animals. So I'm going backward with this presentation because we actually did a multi-animal model, and this was the first model that we actually did. It's called SMAL, and we scanned toys of different species, and we learned this shape space over different quadrupeds. And here you see how here I'm changing these betas, and you can create the different species. And if we look at the shape space in this case, so the average animal, let me go back. So we scan 41 toys for 5 families. So we have lions and tigers, hippos, cows, we have 3 dogs, few wolves, zebras and horses. So the average of these quadrupeds doesn't look like any of them. Again, the first dimension of variation is size, and then you have maybe from horses to tigers, from hippos to horses again. If we take the betas and we project these betas in a 2D space, we see clusters for the different families. So here are all the training horses and zebras. They live together. And here are the cows. And so we have these localized spaces for these families and a lot of empty space around. So typically for using, and then given we have all this empty space, if we sample random betas, we will end up with animals that do not exist, because most of the time they're just interpolation between the different species. So the way to use this multi-species model, the way we did it 10 years ago, was to fit the model to data with an optimization, but specifying with this function a prior for the shape. So if we know it's a tiger, we want this function to say stay close to the cluster of the tigers, and so on. So interesting, recently, some people have taken this energy minimization fitting procedure and created a very large data set by fitting the small model, the animal model, 2 images. And here are all the species this paper called Animal 3D has considered for the 5 families in SMAL. So the dog family with all these different dog breeds, horse, cow, hippo, and tiger. And tiger means also lions and so on. So now we have a like the key point, multi-species data set. We have a 3D multi-species data set. And this group has introduced a network which is called Animer, which is able to do this reconstruction by just a simple network regression. This is not optimization. They train the network on this animal 3D data set plus other data sets. And now you provide as input an image of, a horse. You don't have to say it's a horse. The network understands the horse and gives you back the 3D that aligns with the image. Okay, this is, I was very excited about this because when people use your work after many years, it's really nice. But then I saw this a few days ago. This, I'm sorry, is in Italian. But so this was in the news, in the national news. it's a good news. In the Nashville Zoo, there's this newborn. This is called aardvark. Maybe there are so many bad news in these days that they thought, okay, this is a great news. And this reminded me about this slide from Sarah Berry. She was plotting the distribution of the frequency of the images in the iNaturalist data set, observing that biodiversity has a long tail, and there are species that are interesting for us, for people that work on conservation, where you have very little, you have a very small number of images in data sets. And here she actually puts the aardvark as an example of this rare animal. So now we take the aardvark and we run Animer on it, and we obtain a cow. And this is because, I mean, maybe the cow is the most similar animal, which is fine. The Animer is for those familiar animals, but it would be not useful for aardvarks. So the question is, can we represent these uncommon species with the small model? We saw we have a lot of empty space in the small model shape space. So could it be that the aardvark is here, or maybe the llama is here, right? So how can we find out? So if we want a 3D model of a llama, what will we do? We take an image of a llama, and then we fit the model to it. And this is what we obtain. So this is the fitting. Maybe I did it wrong, but this is what I got. And then we take this, and we put it in the neutral pose, and it looks like this, which looks completely different. And I've done it many times. Is this one. And so this is a bad result. It really looks like similar to the average animal. So the question is it a bad result because the optimization failed, or is it a bad result because the model cannot represent llamas? And it's the first one. Because last year we have presented this work. This is called AWOL, Analysis Without Synthesis Using Language, where we use language to kind of explore the shape space of the multi-animal model by saying, like, I want a llama, so I input llama as text to AWOL, and AWOL gives me back the shape variables, and then I generate the animal, and it looks like a llama. I mean, surely it's better than the optimization result. And to show that this approach is more general than, than for the small model, we also use it using images as input, and also applied it to another completely different type of model, which is a plugin for Blender to generate procedural trees. So with the same architecture, we can input Acer, the name of this tree, or the image, and then we would obtain the parameters for this Blender plugin to generate the tree. So I call this method AWOL. It's such a bad idea because nobody knows about it. The title means nothing. I just love the acronym, and but people that are interested in animals, they don't find animal in the title, they don't read the paper, and they don't read it because people that look at tree, they have no idea that this exists. So lesson learned, be more like, forget about the acronym and write titles, like more meaningful titles. How does this work? So this is based on CLIP. So CLIP is a model. So we use the latent space of the CLIP model. So in CLIP you have two latent spaces, one for text and one for images. And these latent spaces are aligned, meaning that words in the text space are close if they represent objects that look similar. So you have cow and cat are very similar words, but they're not close in clip. Maybe cat is more close to tiger. So what if we learn a mapping? So we have very sparse points. We have 40 points in our shape space. So meaning we have, well, it's more than 40, I will tell you later, but let's say we have 40 points. So then we have 40 words. What if we learn a mapping between the words and the betas? And hopefully, if we then pick an animal that is not in our training, maybe we will end up having some betas that are some nice interpolation, some meaningful interpolation. That was the idea. The training set for training this AWOL is our set of toys. So we have the name like cow and the shape of the cow. Doberman, we have the dogs from the dog model. So we have more than 41. We took the 41 from the multi-animal model. We added the dogs, we added horses, we also added rat and bear. So we had at the end 145 training samples. For very few of them, we have attributes like baby cheetah, female lion, baby tiger, young lion. We have breeds for dogs. We have 2 poodles. One is small, one is big, but they are called both poodle. And for the trees, we have the examples that come with the add-on, which is it's just these trees. It's about 20 samples. It's really ridiculous how small this is. And for the trees, we have pine, and then the parameters of the plugin for the pine tree. So the network we train is called it's real MVP, and it's a model. We could have used a diffusion model, but we decided to use this type of architecture because it's really structured. Sorry. So this model is, this network is composed by a set of modules that are called affine coupling layers. So the variables are processed through these layers by some of them from the input to the output. I don't know what's happening. Sorry. From the input to the output are just copied as they are, and some are like the form with the scale and the translation operation. And the decision on which variables are transferred and which are transformed is defined by a set of masks that in the original model are predefined. I will stop doing this, sorry. Are predefined. This is important, and I will tell you later why. So we train this on our animals and trees, and then now if we ask for an aardvark, that is what we get. It may be not exactly the aardvark, but this is the best approximation in the shape space of the small model. And then we can ask for other different animals. It has limitations because, like if you want a rhino, the rhino is not in our shape space because we don't have the horns. So it would be outside. But what we get from AWOL, I think, is a kind of a nice approximation of rhinos in the shape space. So the technical kind of novelty that we have in the paper is the fact that we train this mask that select the variables. And if we don't do that, it works, but not as nicely as I think it does. So for the poodle, if we train the mask and then we ask for a toy poodle or a miniature poodle or a standard poodle or a giant poodle, we obtain this size variation. And if we don't do that, we don't obtain this size variation. So in the training set, we have a small poodle and a big one, but they're both called poodle. We don't have attributes, as I showed you before. Trees, I don't know, like trees are very random, but at least we get the palms when they're palm, and we get the, you know, the other like trees of kind of shape corresponding to the type of I'm not a tree expert, so I cannot tell how good this is. So interesting, we can use attributes and try to do some also interpolation in our shape space now. So we can do age interpolation. So in the training set, we have, as I showed you before, we have baby cheetah, and then we have a young wolf. But then if we ask for our llama, like baby llama, young llama, adult llama, old llama, we obtain this scale variation, which I think is very, very interesting. And then we can also be very creative with the adjectives. Yeah, I don't know actually the meaning of all of them, but I think most of them, they make sense. Okay, so now we have created a way to generate a lot of training samples in terms of shape. And now we can do multi-species 3D shape and pose estimation. So now we have the 3D shape. We wouldn't do a traditional rendering of them because now we have generative AI. So if you have a 3D shape, we can generate images with control nets. So like if you have a 3D of a horse, like in this way, you can then prompt a model and create a different version of this horse. So we would have the image and the corresponding 3D ground truth. And we do this in this work that is called GenZoo. So now we sample a random species. So before, you remember that there was a plot similar to this one, but only for the 5 families in small. But now we sample generic of quadrupeds. And then with AWOL and the adjectives, we create some shape variation for each sample species. And then we also sample some pose. We create the animal 3D. And then we condition a generative network to create an image. And during this process, we created a data set, about 1 million images of different species with ground truth. We train a network, which is exactly HMR 2.0, which is a network proposed for humans, and we just train it for the animals. And these are some results in comparison with Animer. For dogs, we do a lot better. You can see it here. But I mean, we're using more data, so it's okay that we do better. For the aardvark, now it's not a cow anymore. Then it has a more realistic shape. This was at ICCV this year, meaning it was done, was also rejected once, so it was done a year ago, more or less. But now we have all these 3D image to 3D method. So I tried a few of them. It's interesting because this one, this Tripo SG with the same image, here you get 3 legs. And for the second method, you get 5 legs. But with the SAM 3D, which came out recently, you get an amazing result, which is really scary and exciting at the same time. So one limitation of this method that are trained on on these generated images is that, at least in our training, we don't support occlusion. So if you take these two images with a tiger, which is occluded by the trees here, and here also this is a crop, the legs are occluded by the snow. So if you apply GenZoo, you obtain this very fat animal with short legs. If you apply Animer, you obtain a tiger, but the size is wrong because the legs are all out of the snow. And the same for this other case, where the tiger is behind these trees, and both GenZoo and Animer, they make it smaller. So last year, we also presented at CVPR a method where we try to reconstruct the whole environment, including the trees and the animal. And I think this is an interesting direction to also go into this direction of reconstructing 3D scenes with the ability of then simulating movement and even, I don't know, night, days. So I really like this work. Yeah, this concludes my talk. Thank you for your attention.
Any questions? Yes.
Me? Yes. Thank you very much. That was lots of very, very impressive results. I have a question about why is this structure linear? I simply don't get why you can move around in a linear subspace and basically only generate animals.
I mean, it's so maybe it's not. Probably it's not linear, but that is the simplest. So we learned this model with only 40 points at the beginning. So it's really a small data set to learn anything.
But even when you're like in these results, it looks like there's it's very little diversity outside odd things, right? And I don't really get why linear interpolation between these things would actually. But it clearly, the proof's in the pudding. It does, right? But it just seems.
No, it's not that we. So, do you mean in the going from the text to the?
No, the betas, right? So when you're optimizing the betas, when you're looking at the betas, like it just feels absolutely remarkable that a complicated shape variation like that is a plane, right?
So
in this mesh space.
I think there are two aspects. First, that is a very simple model, and it might not work. So we have this data term that might be very strong. We have silhouette and the landmarks most often. So this linear model is like our prior, and then it's just a reference. And so we rely a lot on the data to create the animals that match the image. I don't know if that is.
I see. So how are you? So if the image term is very, very important in that case, because I could see, are you initializing the betas very close to data?
That was the point.
Yeah.
That if you for the llama example, that's why it fails, because if you initialize, I don't know, with a 0, right? Then it would fail because, because the space is not. You can imagine that you're in a local minima, and that's a problem.
That's a very good question. They do it a lot on humans. Like you're running PC on like thousands of vertices and reducing that into a linear space, and it turns out that works very well.
Yeah, they have tried more complex models with humans because they have a lot of data, but then at the end, the linear model was the one that was most it was an amazing trade-offs
no,
between
clearly the proof's
the
there,
simple
I think it's-
representation and the power of the model. For the animals, the point is that if it's a single species model, I think this linear model maybe is better, but when you have this multi-species model, I think the linear model is not actually a good one. But we don't have enough data now. But with this generative model, these models that go from image to 3D, I think we'll have the opportunity of creating a lot more 3D data. And then with that, I think we can explore and create models that are more like this cluster thing, would be like more natural and not so enforced by just the training set.
Thank you.
Okay.
There's a question.
Thank you so much for the talk.
I want to focus on, so you, I know the focus of this was mostly on like pose estimation along with reconstruction. Is it possible to sort of do partial reconstruction where instead of the whole animal, we like, is like sort of framework possible to apply to, say, reconstructing different parts of the animal more accurately and like seeing maybe different kinds of morphology? Just want.
So you're saying if I have, like in the last slide, if I have an occluder, if I can, I think with a network you can train with a random occlusion, and then this would teach the network to understand that there's occlusion. For the optimization approach, I think you need to, model the maybe layers or stuff or occluders explicitly and with masks and do that.
Not for
Not
occluders, but like reconstructing specific like body parts, for example, like the slit or something, or
The eyes. So it's more
localized, I guess, than the entire animal itself.
For this, the animal model, the small model doesn't really have a high resolution. For the horse, we have much higher resolution. So I think in that case, we can look more into fine details that might be relevant for this behavior. We don't have, for example, facial expressions in the model, in the animal model, but for the horse, maybe it would make sense to have also that kind of fine-grain representation.
But I guess with a different data set and like using this technique, maybe is it possible as well?
For the horse, given all the investment we've done in terms of resources and time, we'll try to make the model even better. This Varenne was kind of a first step, maybe driven by the deadline. But then it was done with the first 50 horses that we scanned, and now we have scanned, as I said, more than 200. So maybe for the next model we will have more even, more parts.
Many questions.
Do you want to go this way first?
I had a related question. Like you have the horse model from toys and from real data now. How much does the real data help? Can we just go with toys, or do we need real data?
Sorry?
Do we need real data, or can we just go around scanning toys and that will be it?
No, I think we need real data. For the tasks we want to address for horses, this is in collaboration with these horse experts, and we have a lot of contacts with actually people that have research questions that are related to understanding, lameness or emotions in horses. So for that you need very accurate representations. Like I learned that if a horse has diabetes, the neck is thicker. So I think you need to be able to model these variations, which are really... also you want to create a computer vision system that is better than a doctor. For lameness, doctors are really bad at detecting which is the limb that has issues. And so we want to do it automatically, and this requires a very accurate model.
Shushin, do you want to go first?
Thank you so much. It's really impressive. I work on human myself, and just have a question about GenZoo. I think on the human side, a lot of the data up to this point, the ground truths that we have are always obtained using methods such as simplify, where you optimize with respect to key points for perhaps silhouettes. So I'm just wondering why people haven't used methods such as GenZoo to generate synthetic ground truth for humans. And have you tried that? And do you think that would be better, or if there's
Yeah. So for humans, I think people use Bedlam a lot.
Even with Bedlam, I think the fidelity won't be as good as compared to diffusion models. So Bedlam, for example, has its own restrictions, as in you can't really simulate hair.
Yeah, so one limitation of this GenZoo data set is that they didn't check how aligned the 3D was with the image. So if you look at the data set, there are many cases where the alignment is not perfect. So I think there is a lot of room for improvement for GenZoo if one would filter the data and try to improve the alignment. And yeah, I think so the result I show with our work is okay, but it's not perfectly aligned with the data. So, and I think that comes from the fact that there's a lot of noise in the data set.
Yeah, thanks for the seminar. I love your work. It's so great. And I was just so annoyed when you see the SAM 3D results on the AWOL, and you kind of think, oh no, they probably didn't train very specifically on even animals, right? I don't know how many animals they use for training that. So it just makes me think, how important is it to train on animals? Maybe your method is a lot better at getting difficult poses, for instance. So maybe you are actually much better at the space of poses than maybe the space of shapes, because it's very difficult to scan the animals. Anyway, it just makes me think, but it's so annoying, right, that their result is so good. It makes me think, what's better? Is it better to just train a model that's really, really good at going from 2D images to 3D shapes, any kind of shape, not specifically animals, but maybe it will struggle with different poses, or do you still think that it's really good to focus on model-based animals?
Not really. But I think, so what I see we should do is, we can create these models that can do 3D reconstruction, but they will never be maybe super accurate for some complex poses and for the questions that we want to ask. They will be still trained on some data. So if we have some outliers, right? So we want, when I say anomalies, we want to detect the anomalies, and it's not sufficient to say, oh, this is not a regular pose. We want to know what it is. And I think for this type of questions, we will still need some form of optimization because the data would be very, very specific. But this pre-trained model will be super useful for filling in the information we don't need. So these generative models, when we have monocular data, they can give us an initial guess of the 3D that then we can maybe refine to be more realistic, because these have been trained on synthetic data like 3D data. And so at the end, you obtain for the animals, they always look more like toys toy. They have this toyish appearance, which might be better than our. But if you want something super realistic, and I think you have a next step to do.
I just wanted to ask, I think
One thing that I really like about model-based reconstruction is that it gives you
a space where things you can interpret the result. You can disentangle the pose and disentangle the shape variation. You can use that for downstream analysis on analyzing
the motion of the animals and videos. I think that's, yeah.
I think that's one of the advantages of using a model-based reconstruction in this current
state as well. Any other questions?
I'll ask you afterwards. Fair, go on.
Great. I think we're, yes, about time. Thank you very much. Thank